there. And you gave yourself remote access and everything? Okay, thanks. So, how is everybody? I can tell you guys are so enthusiastic today. Oh, someone's honest, saying you're okay. So, you guys ready for the semester to be over already? We just started. Look at all you're learning. Don't you feel like you're learning a lot? Maybe I should rephrase it. Don't you feel like your professor thinks you're learning a lot? I'm just kidding. You should be learning a lot, but you're not. So, anyone got a mission call lately? Anyone proposed or got proposed to? Anyone got a raise? I mean, let's talk about anything good. Yesterday I had a migraine, you know. I'm gonna just try to make you feel better. You know, if you didn't have a migraine yesterday, it was a good day for you. Luckily it came on late, so it was in the evening, but still, if you've ever had a migraine, you know they're not fun. So, yeah. Who's excited for General Conference? Good. Always a wonderful weekend. So fantastic. So, anyone, well, I was going to say, did anyone have tickets to the conference center? But I guess, if you do, you must be real special. You might be giving a talk or a prayer. So, you know, they had some youth speak in the last conference. The patriarch that I received my patriarchal blessing from, he actually spoke in General Conference when he was a deacon. And he lived to be 103. And so I think he holds the record for the person to live the longest after giving a talk in General Conference. Because who else is going to live 90 years, you know, 90 or 91 years after giving a talk in General Conference? I mean, like, maybe one of these two youth that spoke, but still. Yeah, it's pretty amazing, huh? So he was an amazing guy. His name was Ned Church, down in Delta, Utah. So yeah, just an amazing guy. And he knew the scriptures so well. You could tell because in my patriarchal blessing, he quotes like all these scriptures, and have to go through and like, oh yeah, I know where that one is now, and I know where that one is now. So great guy. All right, who'd like to offer a prayer for us? Get us started today. Yeah. Okay, go ahead. Thanks. Amen. Thanks. Sorry, I forgot to bring the microphone over, so I apologize for those online. So, okay. So your homework, it's a little bit simpler than usual. You have the written assignment from 3.3b. So we're going to finish 3.3 today. I know we didn't get to a lot of it last time. And study for the exam. The exam will be next week, 7th through the 9th. And it'll be administered through Gradescope. It'll cover everything that we've covered up to this point, like up to today, includes today. So next Tuesday is a review. So come with questions if you've got questions. There are 2 exams with keys on Learning Suite. They're on their own content page. So please get on there, do both of those. It's one of the best things you can do. Go back over your homework too. Make sure you're solid on all those homework problems. And then come with questions. So I'll have questions to give you, but I'm also free to answer your questions. So, any questions on the exam? You cannot use a calculator or computer. Well, I mean, you will use a computer because it's through Gradescope, but you can't use the computer to do your work. Yes? 7th through the 9th.
I have 4 solutions left.
Any other questions?
I'm honestly tempted just to buy it. It's not even that expensive.
So that,
I'm on mute.
that question was, does Gradescope work like Proctorio? Right now, no, that I know of. I'm still trying to figure out what proctoring capabilities it has, if any. So like the questions will come up and you'll select like the multiple choice ones you'll just select. I think the free response you'll write out and take a picture and load it up. So yeah. Yep. Okay, other questions? Yeah, we're still working on the details, so as soon as I know, I'll let you know. Yes. Right now, we are planning on making it timed. So for 4 hours though, so it should give plenty. It should be a 2-hour exam, but yeah. So yeah, it's not a 4-hour exam to be done in 4 hours. It's a 2-hour exam. We'll give you plenty of time to do it. Yes.
So is the exam like online, like you're entering the stuff like into a little like text box on the computer, or is it like similar like the homework where like take a picture of what you've written or something?
So the free response, you'll take a picture and upload it, but the other ones you should just be able to select, like the multiple choice ones. You just select. I imagine the short answer you can just type in something. I'm not setting that part up, but that's why I don't know a lot. One of the other professors is in the process of setting it up. So, okay. Any other questions?
And you said we're not allowed to use a calculator.
Not allowed to use a calculator. That's right. Yep. Okay. Let me talk about the idea of inverse matrices, and then we'll get into the details about how to calculate inverse matrices, how to use them. So if we have 2 feet per second times 3 seconds, we get 6 feet, right? You can think about this thing as changing. This takes seconds and turns it into a feet. Okay, it's kind of like a function. We'll change seconds into feet. If I know I'm traveling 2 feet per second and I travel 6 feet, how do I figure out how far I go? I mean, how long I was going. I'm going to multiply by 6 feet. I'm going to multiply something by 6 feet. What am I going to multiply by? You know it's got to be a half. What are the units? Seconds per feet. Okay, so this will turn seconds into feet. This inverse one will turn feet into seconds. Okay, an inverse matrix does a similar thing. So here we're back to our famous peanut butter and bread example. This is a rate matrix. All of these are rates. This is 16 grams of protein per serving of peanut butter. This is 8 grams of protein per serving of bread. Okay, all these are rates. And this will take servings, a packet of servings, and will create or help you calculate the packet of grams per protein and grams per fat. Okay, so that's what this matrix does. It takes servings, translates it into protein and fat. What would the inverse matrix do? If I had the inverse matrix of this, what would I do with it? Or what does it mean? What would it do? Someone said it would give us the number of servings if we did what? Well, we have to multiply what by the inverse? Yeah, so if we multiply the inverse times this, we're actually just going to get the identity matrix, right? Because then we will have taken servings and translate into protein and fat, and then the inverse will take protein and fat and translate into servings. So we'll calculate servings, but it'll calculate servings given that we have the protein and fat, okay? So in the same way that this went seconds to feet, the inverse will go feet to seconds. So we can do this calculation here to to figure out how many grams of protein, how many grams of fat. 16 times a half is 8. 8 times 2 is 16. So we get 24. Here we get 5 plus 3 is 8. So if you didn't know this, and you knew how much protein and how much fat you had in your diet or you changed in your diet, then the inverse of this is what you'd use to figure out how many servings of each you did. I know in this context it doesn't seem very compelling, but okay. Yeah, for the idea, I hope it helps. So I'm going to pull up our good friend Bart. Okay, so we just touched on this a few days ago where when you multiply by a matrix, it does transformations of vectors, and you can actually think about it transforming every vector, which means it transforms every point in the plane. So it transforms the whole plane. This is represented by just this picture and how it transforms the picture. So I'm going to pick a simple matrix, and okay, so 2, 0, 0, and a -1. What transformation does that matrix do to the plane, or to any point in the plane? What does it do? Someone said reflects it. Reflects it across what? Across the x-axis. So it reflects across the x-axis and stretches it out horizontally by a factor of 2. Okay, so that's what that transformation does. What would the inverse matrix do? What would the transformation of the inverse matrix do? Reflected across, he said reflected across the y-axis and stretch it vertically by a factor of 2. Will that get this big one right here that's underneath the x-axis? Will that get us back to the original position and size? No. So if you reflect it across the, what do you say, across the y and then stretch it vertically, we're going to end up down there. So we got another shot? Delbert?
If instead of having the 2 that we have in the 1 half, then now we put it back with, now we put it back to correct proportion.
Okay, hold on, right. So he said shrink it by a factor of a half, because we stretched it by a factor of 2 horizontally, so we need to unshrink it, so unstretch it. So shrink it by a half horizontally, okay?
And then multiply the same coordinate that we have as -1, you keep that as -1 because it'll multiply back.
Okay, so we're actually going to do the same reflection. So we reflected across the x-axis, but if you reflect across the x-axis again, you get back top. So that's right. We need to shrink it horizontally by a factor of a half and reflect it again across the x-axis. Yes? Take the inverse of what? In this particular example, yes, but that doesn't work in general. So, and zeros don't have a multiplicative inverse, but if we go to a half here, then that reflects across the x-axis and shrinks by a half. So it should be that 0.500 minus 1 times our original matrix, 200 minus 1 times 0.500 and a minus 1. That should give us the identity matrix. Is that right? 2 times a half is a 1. 0 times 0 is 0. And then 2 times 0 is 0. Minus 1 times 0 is 0. Oops, 0. Okay. Here I get 0 times a minus 0 times 0. And here I get 0 times, and I get a minus 1 times a minus 1 just to get this 1. Boom. So they're inverses. And to convince you of that, so I'm going to take the original and I'm going to put it where our first transformation was. So if I did this and I stretch this out. So this one took our first image that we got, this one that's upside down, and stretched out, and it maps it, and we get back to our original thing. So that's one way to think about what inverse matrices are doing. We'll talk about in detail about linear transformations. We have a whole section on it about thinking about matrices as transformations. But just to understand what the idea of a matrix inverse is, it helps me to think about it as the inverse transformation of whatever the original matrix does. Okay. How do you actually find these things? So for 2x2s, there's actually a nice formula. And for 3x3s or larger, there is a process, and it is quite a process. So if you have an arbitrary matrix A, B, C, D, then the inverse of that is 1 over A AD minus BC times, you switch your D and your A, and you change the sign of your C and your B. Okay, doesn't mean they have to be negative. If this B was negative, then this is going to be positive. Okay, and this is going to be your inverse. If it's larger than a 2x2, then there's no nice, really nice formula to work with. So, so let's test this out in our example. Well, actually, before we talk about that, this number here is called the determinant of a matrix. So this is the determinant for a 2x2 matrix. Other square matrices have determinants. The larger they are, the more complex the determinants come to calculate. But one reason this is called the determinant is because it helps you determine whether a matrix has an inverse or not. So if the determinant equals 0, let me write the determinant of a matrix equals 0, then A has no inverse. Okay. And the determinant has a meaning in terms of transformations. So if we go back to Bart, and oh, wrong one. Okay. So the determinant, the absolute value of the determinant, what's our determinant in this in 2, 0, 0, minus 1? The determinant of this is a -2. You get a -2 minus 0. Okay? The absolute value of this tells you how much the area changes by of a unit square on the plane. So this will take 1 square and it doubles the size. Or if you just talk about a picture, it doubled the size of the picture, the area of the picture. The negative, if the determinant is negative, it tells you that it changes the orientation. So there was an odd number of reflections. So here, if we go from the lower left up towards the sky, over the top, down in front of him, and back, if we do that, we're going in a clockwise orientation. But if we do the same thing down here, so we started down here, went up his back, over the sky to his front, down the front and back, we went counterclockwise. So if there's a negative there and the determinant, that means you changed the orientation of the plane. So it has some meaning. And this helps to make sense why the inverse of the matrix would be 1 over that determinant, because if you ended up doubling the area by a factor of 2, then your inverse better shrink the area by a factor of 1/2. Okay, so that should help to make sense of why that's there. Okay, let's do that. Let's find the inverse of this, and we're going to test to see if it works. So the determinant here is 16 times 1.5, so that's going to be 24 minus 80. And then we switch these, 1.5, 16, and we change the sign of those, minus 10, negative 8. And if we multiply this by 24/8, then we better get a half and 2. Okay, we did this right. If this is really the inverse, because this takes 1/2 and 2, transforms it to 24 and 8. This better take 24 and 8 and transform it back to 1/2 and 2. Okay, so is that what happens here? 1.5 24s, that's 36, minus 64. So 36 minus 64. And here we have negative 240. Negative 240, right? Yeah, negative 240, and then 128, because 8 times 8 would be 64, and then you can double it. So minus 280, 40, 40 plus 128. But we have to multiply that all by 1 over a negative 56. And so half of 56 is, what is that, 28, and 36 minus 64 gets you a negative 28. And then here, I have to add 112 to get to 240, and if you double 56, you get 112. So this is a negative 112 divided by negative 56, so you get your 2. So we do get the 1/2 and the 2. So there's one way to solve systems of linear equations when you've only got 2 by 2 matrices. You've already done this, hopefully, with your WebAssign. For 2 by 2, it's not bad since there's a nice formula, but in general, it's not the fastest way to find systems of equations. So, okay. Questions on this? Questions on the 2 by 2 solving systems of equations with these things? All right. Okay, how do you find a system? How do you find an inverse of a 3 by 3 or 4 by 4 or higher? So what you do is you take the matrix you want to find the inverse of. So this is the matrix we're interested in. We're going to augment it with the inverse matrix. Okay, so this is the matrix we're interested in right here. There. We're going to augment it with the inverse matrix. And then we're going to do row reduction to this whole matrix, and we're going to focus on making this side become the identity matrix. Okay, so we're going to do row operations to do so that this side becomes the identity matrix. We'll do the same operations to this side. And at the end, if we can get this to be the identity matrix, then there is an inverse. And that inverse is what we end up with on this side. Okay? And the reason this works is because every row operation is a simple transformation on the plane. And our row operations here, like this is a big, you can think about this as a complex operation of not just a plane, but actually, we're 3 by 3, so space. This is a complex operation. And every time we do a row reduction, we're undoing some of the transformation that does. And we're putting that information of what that transformation is on this side. So as we undo this side, we're keeping track of all of those operations that undo that transformation. So we end up at the end, we're not quite done yet here. At the end, you'll end up with one matrix that does all of the opposite transformations that this one did. So that's why it works that way. So here I started, and hopefully we'll have time to finish. But one of the things I wanted to do, this is how far, this is even further than what we got with the last class, and I thought I'll just keep it on the board because it takes a while. But one thing I wanted to take a moment to do as we go through this is talk about elementary matrices and how to calculate those and what they do. So, so every row operation can be done with by multiplying by a matrix. And the matrices that correspond to one of our row operations are called elementary matrices. And I know you've had some practice on figuring those out. Sorry, say that again. So the question was, is the elementary matrix for a particular matrix the inverse matrix if it gets to the identity matrix, right? Now, elementary matrices are very basic. So there isn't just one elementary matrix that we could multiply by this matrix and get to the identity. It's going to be a pretty complex matrix. It's going to be a product of elementary matrix, a whole bunch of elementary matrices multiplied together that will give us the inverse of this, okay? But it's going to take, every time we move a step, then it would be equivalent to multiplying by one elementary row. Yeah, one elementary matrix.
So all those elementary matrices together.
That's right. Yep. So here, so he said all those elementary matrices, yeah, multiplied together would be the inverse matrix. Yeah. So, so this, what did we do to go from here to here? All I did was, so I swapped the first and second row, okay? So, what elementary matrix can I multiply by 2, 3, 0, 1, a minus 2, a minus 1, 2, 0, a minus 1, and get 1, a minus 2, a minus 1, 2, 3, 0, 2, 0, a minus 1. So I know WebAssign had you work with some of these, and I know some students in the last class had trouble, so I'm going to walk through some of these. So take a minute and think about that. I'm also going to throw up another one. To go from here to here, we took a -2 times this row and added it to this row. Okay? So there should be another one that we could multiply by a -1, not a -1. 1, a -2, a -1, 2, 3, 0, 2, 0, a -1, and get 1, a -2, a -1, 0, 7, 2, 2, 0, and a -1. Okay, so I'm just focusing on the left-hand side for now. But take a minute, think about these. You can talk to your neighbor if you want about what your ideas are. What elementary matrix are we going to put here that we can multiply by this and get that result? Same thing. What elementary matrix can we put here, multiply by this, and get that result? Okay, so think about that for a second.
So when I was doing this on WebAssign, like I started thinking about like the identity matrix or the elementary matrix when you put it up as like
Okay, take about 20 more seconds.
So, well, the top one, you swap them, so it's like 0 and 0.
Right, you're swapping the first and second row. Bottom row.
But then the middle row. You get like another 300.
Okay. All right. So I'm gonna walk through this the way that I think about it. Maybe it'll be helpful, maybe it won't. So, but I go back to just thinking about the operation, what happens when I match up these three to these three and what I want over here. So some of you may do something similar. So here when I take these this first row, I'm going to match it up to these three values, and I know I want this row to come up there, right? So I would love for this to be 0, the number here to be 0, because we'll make that 0. The number here to be 1, because it's going to grab that 1. The number here to be 0, because it's going to make that 0. And will that work for my next one? This, I want it to be -2, and when I take that over here, these two will be zeros, and then I'll get 1, -2. It'll give me my -2. These three, I get 0, -1. I'll get zeros up and down, I mean at the top and the bottom. I'll get 1 times that -1, and I'll get that row. So that looks like what I want for that first row. Is that what you guys came up with? Okay. And then, well, what about for the second row? You know, this gets translated down to there. So whatever I have here, when I move it up, I better have a 1 for that row. And I don't want this messing up anything. These things messing up anything. So when I multiply here, I want that 2, but I don't want it that 1, and I don't want that 2, or any multiples of those. When I multiply here, I want that 3, but I don't want that that or that, right? Because I just want that to be 3, etc. So it should get 0, 0, 1, 0, 0. And then here, I just want to pull out that bottom row. And so when I translate this and start doing dot products, I really just want ones here and zeros everywhere else, and that corresponds to 0, 0, 1. Okay. So this would be the elementary matrix there. This one's a little bit harder, but we can use what we learned from here. Like the first row stays the same, the second row stays the same. I'm sorry, the third row stays the same. So how can I just keep that first row? So 1, 0, 0 will keep that first row, because when I transpose it and do dot products, these are all going to be 0. These will be 1, and I just get that first row. The bottom, so if I want to keep that bottom row, then the bottom row over here, I transpose it. These I want to have 0, and I just want to have 1 here. So 0, 0, 1. And now here's the hard part. What do I do? What did I do to get this 0? So what operation did I do? I came and I turned this here. I wanted this to be, I got that 0 because I wanted this to be multiplied by a -2 and this to just be itself. And that I didn't use that on the row operation, so I want that to be 0. So here I want a -2 times this and one of those and none of those. So I should have that row there, because that'll get me a -2 of these plus that. Does that give me 7? A -2 times a -2 is 4 plus 1, 3 plus 0. That gets me my 7. Okay. We okay with this? All right. What if we wanted to? Yeah, so we've done the two kinds of operations, this changes this changes the order of the, changes the order of the rows. This will multiply one row and add it to another row. The other one is if you're going to multiply or divide one row. And like if we want to divide this by 2, so we end up with 1 and a minus 1/2. How would we change this row to make it the same as just multiplying this one by 1/2? Yep, just take that into a 1/2. And then when you start thinking about the operation, then you turn that, these two zeros, I mean, you're not even worried about those, and you get half of this 2, which is your 1. And for the next column, you get half of the 0, which is still a 0. And you get half of a minus 1, which is a minus 1/2. So those are your 3 elementary operations. So in theory, we could keep going and write one of these elementary row operations for every single step that we do. And then this first matrix that we started with, we could write down as the product of all of those. Well, it would be the product. The product of all the elementary matrices. Those elementary matrices undo what this transformation does. So the product of all those elementary matrices would be the inverse matrix. Okay, let's keep on going. So here I just switched the rows. Here I took a -2 of this row, added it to this row. We got this. Here I take a -2 of this row, add it to the bottom row. I get this. Then I switched these because I'd rather divide by 4 than 7. So I switched those out and divided by 4. You get that. And then multiplied a -7 here and added to this row. And then we got this. And then I saw I had a 4 here, so like I thought, let's multiply by 4 so we can get rid of those denominators and get that to be a 1. So multiplied by 4. And I also used this line and multiplied by a -1 to add here to get rid of that. So a -1 times this added gets us that row. Okay? And we're almost done. Okay? That took like 15 minutes of the last class. So we're way ahead of schedule.
So on the augmented matrix, are you like changing it a little bit every step, or are you starting, because like every elementary matrix like shows the row application and switching and subtraction. Are you starting from like a blank elementary matrix and adding a new one every time, or are you just tweaking it a little bit here and there every time?
So in this process, so the question was, are we starting with a different elementary matrix every time, or are we just tweaking it every time? In practice, we don't usually write down all of the elementary matrices, okay? So in practice, when we're trying to find it, we're just doing row operations, okay? So we augment it with the identity matrix, and then we're just going to do row operations to this side, which each row operation we could, if we wanted to, calculate an elementary matrix. But whatever operation we do, we have to do the whole row. And so this right-hand side does slowly get changed, right? And we're almost to we have 2 more operations, and we're going to be done with this. We're going to have the identity matrix on this left-hand side, right? Does that help? Okay. At what point did I know that the elementary matrix exists? I mean, sorry, not the elementary, that the inverse matrix exists. At what point in this process could I stop if I just wanted to know if there's an inverse matrix? Where could I have stopped?
We have basically the ones across. So now that you can make all the other ones 0,
All right. We've got a pivot column. I mean, we've got a pivot position in each column, or pivot position in each row. We're good. Maybe technically we could stop here, right? Because even though this isn't 1, we have the pivot positions. Very nice. Okay, there's a question. Okay, yeah. So once we see that we've got pivot positions or our rank, we have a rank 3 matrix over here, then at least we know the inverse exists. We still don't know what it is yet. We have to keep on going. So, okay, well, let's finish this off. So let's add this third row to the first row to get that element to be 0. So 1, a minus 2, 0, 4, 6 plus 1 is 7. A minus 7 plus the 0 is a minus 7. 0, 1, 0, 0, 0, 1. You can just repeat those. Minus 1, minus 2, 2, 4, 6, and a negative 7. Okay? Now we're one step away. So if I multiply this second row by 2 and add it to the first row, then I would get 1, 0, 0. So I'm multiplying by 2. So here I'd have 4 minus 2, so that would be 2. Here I'd have 7 minus 4, so that would be 3. Here I'd have a negative 7 plus 4, so that would be a negative 3. And these other ones stay the same. So did that kind of fast, but I'm confident in your row reducing abilities. I'm just not confident in my own. You didn't see how many mistakes I made in the last class trying to do this. So those fractions, man, just kidding. We can handle fractions. Okay, so this is the identity matrix. This, not the identity matrix, the inverse matrix. This is the inverse matrix of this thing. Okay? So if you multiply those two matrices together, they better come out to the identity matrix. So, and we can check at that a little bit. So if I take 2, 3, and 0 here and multiply it by 2, a minus 1, and 4, then I get 2 times 2 is 4, 3 times a minus 1 is a negative 3, 0 times the 4 is 0. So I end up with 4 minus 3, and I get a 1. And if I take that, if I take 2, 3, 0, and multiply it by the next column, then I get a 2 times a 3, which is a 6, 3 times a negative 2, which is a negative 6, and a 0 times a 6, which is 0, I get a 0. And you can keep going, and you'll end up with the identity matrix. Okay? And you do the same process for any size, 4 by 4, 5 by 5. In practice, this is not a great way to solve systems of equations, but you can. Okay? Any questions?
So for anything over 2 by 2, there's no other way we can do that.
Yep. I just say there's no other way. You can count. You can find out the inverse matrix every time. I mean, the elementary matrix every time, and then multiply those together. But this is the standard way in doing it. So, yep. Other questions? Okay. But I've got a question for you. Why would an inverse matrix not exist?
If the determinant equals 0.
So why would it not exist if the determinant equals 0?
Because you can't divide by 0.
You can't divide by 0. If I deleted that, I deleted the equation. Okay, so it can't exist if the determinant equals 0. But any matrix I multiply, can't any matrix? I can multiply by a vector and I get a new vector, and any matrix I can think about as a transformation. So can't I just undo that transformation that this one did? What if it's all zeros? And what if it's all zeros? Then where every point in the plane or space goes to where? The point 0. And you've lost information. You don't know where, how to translate all those points that got mapped to 0. You don't know how to put those back where they started. So there's this issue of like invertible matrices I mean, yeah, invertible matrices do a transformation that you can always undo. You haven't lost any information. There's a question here. Yes. Let's go back to Bart, see if he has something for us. I really hate using Bart because I don't like Simpsons. Rude and crude. I should make my own here. So yeah, I didn't make this. I just pulled it up. So yeah, I wouldn't have put Bart on there if I made this. So yeah. So what do I? So I'll just make it. Let's do 1, 1, a minus 1, a minus 1. Okay, we're gonna make that matrix 1, 1, a minus 1, a minus 1. What's the determinant of that matrix? 0, because you get a minus 1 minus a negative 1, which is a minus 1 plus 1, which is 0. What else do we know about that matrix? About 1, 1, a minus 1, a minus 1. What do you know about these columns? What do you know about these rows? They're identical. So these are identical. Yeah, the rows and columns are linearly dependent. Okay. So let's see what happens when we do this. So let me get A to 1, B to, what's B? A minus 1. What happened? It turned into a line. It took 2 dimensions of information and it collapses it down to 1 dimension. Can you undo that transformation? No, because you get infinitely many points that get mapped to 1 point on the line and you can't undo that. Okay, so that's what happens when you have rows or columns that are linearly dependent in a matrix, in a square matrix. The transformation reduces the dimension and you're in trouble. So the number of free variables is the number of dimensions that you lose. The rank is the number of dimensions that you keep. So yeah, there's different, those are connected to ideas that we've seen before. So yeah, this gets collapsed to a line and then you can't undo that. So we don't know where, where's his right pupil at? I don't know, or like the right pupil gets mapped to some place, but also a whole bunch of spots on that picture got mapped to that same place. Can't undo it. So, okay, questions? All right, thanks, Bart. You've done something good in your life. I'm just kidding. We can all repent. So, okay. I'm going to pull up. We have one more thing to talk about. The invertible matrix theorem. So this is the fundamental theorem of invertible matrices. Sometimes we'll just call it the invertible matrix theorem. There's more here than was in the end in 3.3 in the book. And we will continue to revisit this because as we learn more and more about matrices and have new and new ideas, we'll see that a lot of them can be stated as the equivalent of a matrix being invertible. In fact, there's one we've already talked about today, and it's not even on here because we haven't really focused on determinants much. But if the determinant is not 0, then A is invertible. So that's another one. So all of these are the same. So if you know one of these, you know all of those. If one of these is not true, none of the other ones are true. Okay. So A is an invertible matrix. A is row equivalent to the n by n identity matrix. So we use that fact to try to find the inverse matrix here as we start doing row reductions to get to the identity matrix. And if we can't, then we know that it doesn't have an inverse. Yes? Row equivalent means that it can be 2 matrices are row equivalent if you can do row operations to 1 to get it to be the other one. So good question. A has n pivot positions. Since we're only talking about square matrices, if you've got n pivot positions, then each column is a pivot column. Each row is a pivot, has a leading, leading coefficient in it. The equation AX equals 0 has only the trivial solution. that means, like, if you think of taking linear combinations of the columns of A, if you have to have the coefficients of all those be 0 in order to get 0, then we know that that's equivalent to saying that the columns of A are linearly independent. So the columns of A form a linearly independent set. We could also say the rows of A form a linearly independent set. That's also another equivalent one we can throw up here if it's not already. AX equals B has at least one solution. The columns of A span Rn. So you're in n by n space. If you span the whole space, then you're good. Yep, then you're toast, right? So yeah, if you have one row of zeros, there's a whole bunch of things we can put up here. Oh, well, it doesn't have n pivot positions, right? You can find a solution where it's not a trivial solution, right? We know that the columns would, or rows would not be linearly independent. So yeah, very good. There's an n by n matrix C such that C times A on the left is the identity matrix. And also there's a D that you multiply on the right. Those, we know that if there is one, that C and D would be the same. So, and that would be the inverse matrix. There's only one, there's exactly one inverse matrix for an invertible matrix. There's only one inverse matrix. Like if this matrix is invertible, if this matrix isn't invertible, there aren't 2 or 3 inverse matrices out there, or infinitely many. There is exactly one inverse matrix for this, okay? So that's why we can just make the notation A to the minus 1, because it's exactly, there's only one of these, so we'll just say A inverse. So,
So here, if they're true, C is the inverse of A, and B is also the inverse of A.
yep. Yep, but if you can show that, hey, there's some one that you can multiply on the left and get it, then you know it's invertible. And so then you'd know there's going to be one on the right, and actually they're going to end up being the same. So you raise your hand? Okay. And the transpose of A is an invertible matrix. So I claimed that that if the rows of A form a linearly independent set is another one, here's my proof. Okay, if I already know these other ones, then I'll say, I know the columns of A form a linearly independent set. Look at A transpose. Now the columns of A are now the rows of A transpose. And since I know the columns of A are linearly independent, now the rows of A transpose are independent. So that's my proof that we could put on the rows of A from a linearly independent set. We could put that one on there too. Yep.
For the proofs on the homework, I mean, like the homework that we just had on the Tuesday, there was a couple of prove that the inverse of the identity matrix is the same thing as the identity matrix and stuff like that. Is there multiple answers and you could use this to either prove or disprove?
Yep. Yeah. Yeah. Especially that identity one. There's like tons of different ways you could prove it. You could prove that one. Yeah.
So that's basically what we do for the proof. We use these.
Yeah. So you could use any of these, and you could have said, hey, A has n pivot positions. You could just multiply the identity by itself, and you get the identity and say, well, I found one that I can multiply by the identity and get the identity, and it's the identity. So yeah, you could do any of these, any of those things. Yeah. So yep, good question. Any other questions? Okay, have a great weekend. Study hard for the exam.